Thank you so much, Aleksandar, as the first chairman of this session. We can start the session. Enjoy.
Okay, so welcome everybody. I hope you can hear me.
Yep.
Okay. Who can't hear me, he or she should say so. Okay, I hope everything will work fine, and we can start. The first paper is from Russia, if I'm not wrong, somewhere far away, and this is why you switched to be the first one. You have a couple of hours more than we, I guess. So the first author is Smolin, and the question is about, at least from my side, about a diagram which appears at about 8 minutes. It shows values of incremental z, that is movement in vertical direction, I guess, divided by L, which is constant value, and these two should be the first one in the range up to 3 millimeter and the second one 0.7 millimeter. So when you divide them, it should be about 4 no units, but on your diagram X scale states something like 0.007. So please explain, maybe it's just a simple mistake or I have overlooked something. It's your...
Yeah. Actually,
yes,
on horizontal axis, we put dz, that is incremental of the motion of central part of the beam. So it is just deflection normalized by the length of the beam. So it is small direction, a small flexure. So it's okay, I think.
Okay, but then values are wrong then, because your dz is from 0 to 3 millimeters. When you divide that with 0.7 millimeters, you should have something from 0 up to 4.5 or 5 unitless. And you have something up to 0.0007. Can you check it? Of course, we don't have to solve it right now. Yeah.
Yes,
okay.
Right
okay.
Now, yes. Thank
you. No problem. You can do it later, and if something is wrong, you can correct it. It often happens when you plot these diagrams. Okay.
Sure.
Is there any other question for the paper on simulation of 3-point bending and so on by Smolin and his co-authors? Presumably there are no more questions, so I will maybe give a chance to the authors if they want to something to add any comment on their paper.
Yes, it's small comments that it is just the beginning of the big research, I think. So it is the first step in the model building and trying to, say, study this complex system, because nitinol is a shape memory alloy, and so we have to take it also into consideration, but it will be done later. Also, the current model for the silicon coating is also simple. We should improve it for better corresponding to the experimental results. So that's a comment. Okay. Thank you.
Okay, let me also say that I like this paper. I think it's very well done. A very important research, a new one, original one. so I can encourage you to continue on working. And just tell me, Tomsk, is it? Where is Tomsk?
It is Western Siberia, so the time shift is 6 hours with
Yes, so you
Rome
are.
and with Belgrade and so on.
Yes, so already after lunchtime. Okay. Thank you, Tomsk.
Thank you.
Thank you.
So we now stay in Tomsk in a way because paper by Eremina and her co-workers on numerical study is next one. We do have at least one author there, isn't it?
He's there.
Okay.
Yes, Galina is here.
Oh, Galina Eremina is right there. Okay. So we just continue with the same team, with the same screen. Great.
Yeah.
Thanks.
Right.
So somewhere at about 10 minutes, there is a diagram force versus time. I guess you can find it. It is quite interesting diagram, but I have two questions. First one is, how did you get it? Is it just simple experimental record or what?
No, this is simulation results. For different kind of loading, yes, so the angle of the force applying force, and we have different response of the system. Yeah. So is it just
yeah, okay, that's a better option because my other question is maybe a bit complicated. So it is a bit strange for me that maximum force for jogging is slightly lower, not a big deal, but slightly lower than maximal force for standing and walking, which I don't think it's in reality like that. Can you comment on that?
a little bit small?
A little bit small. A little bit small.
Yes, a little smaller, yes. But why? Maximum force should be higher for any kind of jumping, even small jogging or
I think because the jogging is running with small steps, so it is actually maybe a dynamic loading, but it is not so big because jogging is not running with the fast speed actually.
Okay, but it should be more difficult, should get higher maximum force than just walking, or at least standing. It has to be worse than standing. So please check your model then, please.
Yeah, maybe we will see. Thank you.
This is yet another paper that I really like. It is fascinating, this simulation, and of course these biomedical applications are always very important. So it would be of a big interest and importance that you continue working and maybe find out if something is in this modeling not exactly as it should be.
Thank you.
Thank you.
Okay, thank you, and then farewell to Tomsk, at least for this questioning. Okay, so now we shift our attention to the paper number 3 by Danek and his co-workers. It is analysis of selected parameters and so on. It is from Katowice, if I'm not wrong, so hello for Poland. And my question is for diagrams, which appears in between 5 to 8 minutes. These diagrams should present stress distribution, but they are all in blue color. I don't see any other color than blue. So I don't see any stress distribution. It's probably just a matter of not very well presented figure as the output of the software, because values seem to be correct and they are given in the paper, but I would like to hear a comment on this, if possible.
I think the problem could be with the scale of on the diagram. I'm not sure which one. It's slide. It's slide with boundary difference.
All of them. All of. Actually, we don't see in neither of them. We don't see red color. It's there is green, not only blue. There is something green, and we can identify the zone, which is important. Scale of the zone with the deformation. That's very important, and that's good enough. But just if you can comment, why don't we see any red color, any maximum stress, and where are they? Where are the maximum stresses actually? All diagrams.
Okay, I think the problem is with the how it was modeled, because we modeled this composite material as 10 separate layers, but this diagram show only top view of this. So I think the red color could be in the lower layer. So maybe it will be good if I show the maximum value also on the diagram.
Yes, that could be the case, and I would also suggest then that you more explicitly write that what you represented here is the model with 10 layers, not the one that contains only one layer. That is somehow okay, one can guess, but it is not explicitly written, and that probably is the cause of not being able to see red color. So, okay, thank you.
Thank you.
Any questions for the paper by Daniek?
Hello, I have a question. May I interrupt?
Yes, of course. Please
hi,
do.
Dominic. Thank you. Hi. So I just unmute my microphone. I want to make sure that you hear my voice.
Yes, we do.
I had a general looking in the presentation. I just wanted to know, based on the shapes, did you use Aleksandar for modeling? If yes, what type of material you used for the modeling and simulation of your composite materials? Thank you. I mute my speaker.
Okay, I use Aleksandar and Lagrange finite element method implemented in this software was used. It's the bullet or impactor was modeled as rigid body, and it's dependent case, but composite material was modeled as one layer or 10 separate layer. In case of modeling of as 10 separate layer, it was modeled because we would like to see the lamination process in this material.
And may I continue, if the low density is changed to high density, you would use the same type of material or no?
Can you repeat it, because I can barely hear you?
Sorry. If instead of low velocity, it was like high velocity, would you change the material type or you stay in the same type of material?
We only considered low velocity impact. Maybe in the future we will use, consider also high velocity, but for now we only consider low velocity impact. So we use. Okay, so I have little problem with the voice here. Did you hear me?
Thank you very much.
We can hear you.
Okay, thank you.
Okay, Jamal, is that all? Thank you, Jamal. Any other questions for Daniek? If not, we go to the next one. It is Campillo, if I'm not wrong, with the last name.
Yes, correct.
And thank you. And co-authors on numerical modeling and experimental and so on. We have here, I think, at least 3 countries as contributors, Italy, Spain, and France. So hello, Italy, Spain, and France. And my question would be about eventual crack propagation. Namely, I couldn't find in the paper itself anything definite about was there any crack propagation or not. And then again, you stated that you use XFEM, which, as far as I know, is used for crack propagation. So please, can you comment on that? What XFEM was used for in your research?
Yes, hello everyone. Hello. First of all, I would like that we are from Portugal. The 3.
Oh, I forgot Portugal, of course, as the main country. Sorry.
Yes, regarding we are using the models of Abacus, the XFEM formulation that exists. I don't have pictures in the paper about crack propagation, but we consider crack propagation as
Can you repeat the last sentence? It was not very well. We couldn't hear it. Just
Of course, we are considering crack propagation by the algorithm that exists in Abacus.
Okay, so there was a crack propagation in your research. Okay, then please state it more explicitly when you write the paper. Put some more details on crack propagation, please. It is very interesting, very good paper, and we need just more information. How was that simulation done?
Okay, sure, I will put
Okay. Okay, thank you. Thank you, Porto. We had a lovely conference there last year, and I'm sorry that I forgot to mention beautiful city of Porto. Now, any other questions for Porto? If not, we may proceed. We can go now to high fidelity numerical and so on, which is by Biancolini and his co-authors.
Hi.
Hello. And my question is once again about XFEM, but this time it is completely different question, opposite question. Now I'm asking you, why haven't you used XFEM? Have you tried maybe XFEM, or what is the reason that you haven't used it? Is it a problem with the modeling of surface crack growth or something else, or you simply didn't want to use it?
Okay. Hi. First of all, thank you for the question. And shortly answered, no, we haven't tried XFEM. Also because we have started this work on crack propagation with a push on the application side, since we were asked to develop this method by employing widely commercial softwares used also in fusion for energy. And so for this reason, we started working on plain FEM softwares. This is why. Also, in our research team, we are focused on using radial basis functions. So we found out that it was the good way to use FEM and radial basis functions. However, we are developing now methods to exploit FEM results in a meshless fashion by enriching the solutions using radial basis functions, using balance equations, and evaluating the crack propagation in a meshless fashion, evaluating the J-integral meshlessly. So it is not actually XFEM, but we are moving in that direction, but starting from a commercial software that is also an FEM widely used commercial software, of course, that is more easy achieved as a calculation.
Okay, thank you. This is a rather complex problem, and I can encourage you to work it out and to try all these different options. It's very good paper, very good research. And just to correct myself, this paper is coming from Italy, France, and Spain, not the previous one. The previous one is Porto. Okay, any other questions for this paper, please? Okay, no other questions. So
thank you.
Thank you once again. And we move now to estimation of multipass welded joints by Luca and his co-authors. It is very interesting work, very practical work, but I have one important question about slide 13, one of the last slides. That is the slide which shows displacements, if I'm not wrong, or strains, whatever, which is the main purpose of the paper. And there is a comparison between numerical and experimental results, if I got it right. But that comparison indicates a big disagreement between numerical and experimental results, if I got it right. For example, there is 0.11 versus 0.46 above, and below at the joint, welded joint, there is 0.19, and compared to that 0.01. So did I get it right? Is it really such a big disagreement between numerical and experimental results, or maybe something else is in the question? So whoever is in charge, please reply.
Can you hear me?
Yes.
Yes. These on the slide, the last slide, are the displacements in millimeters. So in let's say in a relative value, there is a big discrepancy between numerical and experimental values. But in absolute values, the error is not quite big. The scope of this method is to at least estimate the magnitude of deformation. It's a very fast method compared to computational welding mechanics, but the cons of this method is a lack of, let's say, precision. But if the order of magnitude is right, we can, let's say, use a more precise method, but it always it will cost more in terms of computational time. So we we said we are fine with these results because we understood that no further action were necessary before the start of production. This is actually this is like a real megastructure joint. They were made like 60 of them, and it was just a prevision of the order of magnitude.
Okay, I agree with you. If you look it that way, if you look as let's say megastructure, and then you just look at the absolute values, that's quite fine result in that sense. And this novel method that you introduced, that you can analyze every single welded joint in a megastructure, is really very important, and I think application is really impressive. I just forgot to say that this paper is coming from Italy mainly, even though Filippo Berto is involved. He's from Norway, but he's Italian. So once again, hello to Padova, and for everybody question, do you have any other question, please? Well, if not, we move to Greece. It's just across the sea. So from one ancient to other ancient culture. Hello, Greece. Computational analysis and so on. Very, very interesting paper. I like it, and but I have one more out of curiosity question. It's not exactly expert question. It's something like you mentioned at one spot that metallic materials are intended for anti-seismic and application and aircrafts, whereas polymeric are for biomaterials. Well, that sounded a bit strange to me. On what basis have you made this distinction? Can you comment on it? It's not very important for the paper itself, but it just attracted my attention.
Yes, we can understand this. We want, when an earthquake is on a building, we want to handle, the movement of the building. So that's the reason we want to use a metallic material for that reason. And when an aircraft is on air, the turbulence of the air on the wing is very high, extremely high. And the very low temperature, minus 56 degrees of Celsius, it's very strong, and we want a very strong material for that reason. For the polymers, now on surgery they use 2D lattices for that, when they want to, a trauma to, to bond it. Yes.
Okay, thank you. That was more academic question than expert one. Now paper is open for discussion. Do we have any more questions for computational analysis and so on?
Aleksandar, we have the question from Marco Maurizi.
Okay, yes, you're right. So at slide 25, it seems that the behavior of the shear modulus with the pentamode Rhodes diameter for the polymer is the opposite of that of the steel, looking at the x-axis. Any comment of that? Oh, mistake, okay.
I'm sorry, I'm very sorry about that.
So mirror image actually should be the right one, I guess. Okay, you will. No problem. You will corrected. This is what discussion is for. So thank you for Marco who noticed that. Any other question? Okay, if there are no more questions for our friends from Greece, we can release them. And we now turn attention to the next one, which is by Marco Maurizi, who noticed this small mistake. Now, this is on 3D effects on fracture mechanics. A very important paper, very, very good paper. And what is maybe missing, at least for a discussion purpose, is what real problems, can you tell us at least one or maybe a few real problems that we need to take into account K2 and K3, that we really need these 3D effects? That's my question, and we'll see for others.
Hello to everyone. I'm sorry for my voice, first of all, because I'm flu. Anyways, as I reported in the presentation, for example, we have problems in the failure assessment in mixed mode 1 and 2, and I can say that in every case we have in plane shear load. There is a coupled mode 0. Therefore, for example, in welded joints, we can mode 0 can occur, and also in the case of angular corners, like with an angle greater than a certain value, about 102 degrees, so where the singularity of the mode 2 disappears, we can have mode 0, which is still a singularity. Therefore, it's important in real problems to understand this, and this is only an example in welded joints. Otherwise, in my short academic experience, for example, in lattice materials, we have nodes, intersections, and there is a multi-axial stress field, which could lead to a failure due to a coupled shear modes. This is, I think, briefly my answer.
Okay, thank you. Marco, you are now in Trondheim, aren't you?
Yes, I'm in Trondheim.
You are in Norway. The paper contribution, this contribution is from Norway, so hello to good old friends in Trondheim, Ente and you. But this is not exactly what I wanted to ask you. We know that what you explained is, how to say, theory. My question is, from the practical point of view, can you tell us an example where we really need K2 and K3? In my experience, when we had cases with fatigue crack grow in some complex three-dimensional structures, we had to take into account K2 and K3, but that's a really rare case, not so often. So do you know, theoretically this is fine and I like it, but do you know any real problem? Have you done any real problem that you calculated K2 and K3? Not academic problem, but real problem, some structure.
Yeah, some structure.
Or maybe you will do it later.
Yeah, we are working on that. Anyways, like as I said, in lattice materials at intersection, there like K2 and K3 are important, and like the singularity due to the couple mode 0, mode 3 could shift, as I report in the presentation, could shift the failure location, and that's important for the understanding of the process, for example, for the fatigue crack initiation location in plates.
Okay, thank you, and my best regards to Filippo. Any other questions for this paper? If not, we are grateful for contribution from Trondheim, and we shift now to the next one. Thank you, Marco, once again. We now focus attention to numerical investigation by Tashkinov. So we go back to Russia, to Perm, which is, I guess, closer than Siberia, than Tomsk. And my question would be similar to already asked at the beginning of this session, namely 8th and 9th minute. There are figures, very important figures, but they are all in blue. In this case, I actually mixed them up with the previous one when I asked all in blue. So we don't see any stress distribution actually, and it would be very important to really see it. Once again, numbers are okay, they are presented, and this analysis is excellent, everything is fine. We just don't see distribution. Any comment on that?
Yes, I would like to comment that. Hello to everybody. Can you hear me? Yes?
Excellent.
Well, I just wanted to say that actually I think it's some technical problem because in my paper actually pictures from these videos, they are fine. So I think it should be videos actually, not pictures. It should be videos. And I think they just didn't play well or something like that because, well, it's strange because in the file that I uploaded, they were fine. Probably something happened in between. So, well, I'm actually sorry for that because I actually wanted to show the videos, but if they didn't run, actually sorry for that. Well, probably I did something wrong. Yeah, but this picture actually shows damage field distribution in case of different loadings and different volume fractions of the volume that we have studied with our method. So, the main conclusions that we can make from this is that, volume various geometry and various morphology can play a huge role in actually damage process. And these pictures were to illustrate that, yeah, but unfortunately, if you can't see them,
okay, that's not a big deal. Yeah, not a big deal because this is just a presentation uploaded and who knows what happened. It's important is that we really will be able to see once you write the paper. That's important. Yes. Okay, thank you, Mikhail.
Thank you. Thank you.
Now for this paper, we have another question, if I'm not wrong, by Andrew Grguch. Question is for the diagram which appears at about 2 minutes and 26 seconds. It is about 15.7% of porosity. Following this UCS on the curve, the stress decays. There is a small jump at the beginning, actually. And the question is, can you maybe say a few more details about it?
Well, is it a curve about force displacements or strain stress curve? Which one? I just don't know which one they are actually referring to.
Can you find the slide on 2 minutes and 26 or so seconds?
Yeah, sure.
And there is a diagram.
26.
Okay, it's count versus gravity scale value.
I'm not sure this is from my presentation because well, I don't have such picture actually in my presentation. I think this is something.
Okay, maybe I mixed it up. Sorry if that is the case. Okay, as we can see it, it should be at your presentation.
Really?
But
well, on 2 minutes 26 seconds, I have an experimental characterization picture with.
Yes, and there is a diagram.
Ah,
That's correct. There is a small diagram. Yes, yes, yes.
In the middle.
Yes, yes,
Well,
yes.
I
That's the
see,
one.
I see now.
Beginning
Sorry.
of it.
Yeah, yeah.
Yeah, no problem.
So in the middle, yeah, so it's called thresholding. Yes, this one.
Yes, that's the one.
Okay.
Yeah. So the question is, what happens in the beginning? Why it goes up and down?
Well, this actually was taken, this picture wasn't obtained by ourselves, so it was taken from the paper. But this picture actually, I think it was taken from the experiment where these pictures were subsequently obtained by going from one side of the volume to another one. So probably at this side of the volume, they have, well, a larger amount of phase in comparison with the other. So so I think that 0 to 100 is the length of the volume. So they just went from the and they counted the actually volume fraction. So probably that's why is the matter.
Okay, okay. Thank you.
Thank you.
Andrew, do you have any comment? Because you asked the question. Of course, two of you can communicate later on about on this, of course, as well.
Sure, thank you.
Okay, good. Now, do we have any other questions for numerical investigation as just presented? Okay, if not, thank you, Mikhail, once again. And bye-bye for Russia for now. We go back to Porto. We go back to beautiful city of Porto. We have paper by Parahani and his co-authors. It is an overview of the stress in, and so on. And it's very interesting paper with the comparison of a couple of different ways how to get K1. There are at one point four different values due to four different ways how to get K1. And these are according to ASTM, according to digital image correlation, to finite element method, and compliance method. And they are all very close. It is a relatively simple case, but it's quite interesting to have comparison like this. But my question is, out of these four values, which one you consider to be the, let's say, the closest to the real value, or the most correct?
Hello. Can you hear me? I'm Bertrand.
Yes.
Okay.
Yes,
thank you very much.
We can hear you. Yes.
Yeah, thank you very much, Mr. Chairman. Actually, the result that we obtained for the stress intensity factor is from different methodology. For example, experiment, numerical, and also, let's say, compliance is a kind of analytical solution. And a good verification was obtained between the result, but I think DIC and STM, which is the reference, produced a better result.
Okay, I do agree with you because DIC is experimental one, ASTM is really a reference one, which is quite well elaborated, and these two are really, really very close. Okay, exactly. Thank you. Any other questions for our friends from Porto? Okay, if there are no more questions, we can say farewell to Porto. And now I will stay right here in Belgrade. You can see another face on the screen, I guess. This is Simon Sedmak. He happens to be my own son. and we are using one computer for this. So numerical simulation of a large pressure vessel, kind of a prototype and so on. And my question for him is about the boundary conditions. They are clearly stated. That's not a question. Question is, how sure are you that they really represent the real case? Obviously, it's not exactly how in reality this prototype would behave, but I guess you can explain why they were defined as we see in this presentation. So Simon, please.
Hello everybody. Well, the basic idea was to try to get the numerical simulation to deform in with as much similarity as the real prototype. So we removed some of the constraints to allow it to, so to say, inflate properly. So the first idea was to, of course, one end had to be fixed, so we would avoid the whole model sliding along one of the axes. And the idea was first to remove both of the axes that form the cross-section plane, but doing that didn't make any difference. So we just decided to remove the constraint along the y-axis because we would get better deformation that way, more realistic looking.
Okay, so although a bit artificial at the first glance, you are sure that stress analysis is actually correct, and I do agree with that. I just believe that somewhat more detailed elaboration on it should be even put in the paper.
Well, there was a lot of work with those boundary conditions until we got them right. It wasn't so obvious as usually.
Okay, so you can also refer to your previous papers on this issue.
Yes.
Any other questions for Belgrade? We are both here now and looking forward for any other questions. This is, by the way, the last paper in this session. And we are well with time, 45 minutes. I think we are excellent with time. Maybe coffee break will be available.
Okay, if there are no more questions also about the other papers, we can have a little break up to 10 o'clock and we will start again with the second session. Enjoy a drink on the coffee or something like that. Okay?
Thank you, Francesco.
The platform will be always open.
Thank you.
And we will
Ciao,
be back
Aleksandar.
here at 10 o'clock Rome time.
Ciao, everybody. Oh, Filippo is there now. Hello, Filippo.
Yeah.
Oh.
I was always here. I was always here, but silent.
Oh, okay. Great. We like two papers that you are co-author.
Thank you so much.
I wish to thank Aleksandar for his contribution as a chairman for this session.
Yes.
Thank you, Aleksandar.
Yes, excellent.
You're welcome always. I enjoyed it. I think it was very good session, and I think this way of doing it and making a conference in this way is actually excellent. And of course, we can't replace reality 100%, but this is really close. I had a feeling as if we were all together in the room.
Yeah.
Yes, I agree.
Bye-bye.
Okay, let's have a break, 10 minutes.
Okay, bye-bye.
Thank you.